Hello, I'm Matt, aka Bob the Giraffe Monkey, and this is going to be my second version of tutorials for parity plus cube shape on the Sq-1. I made some before, I didn't finish the series, but I'm going to improve them hopefully. So in this video I'm just going to talk about a bit about what it is. So you have a Sq-1, it's going to be randomly scrambled with some shape that probably isn't cube shape, and the goal is to get it to cube shape and solve parity at the same time. That is, force an even parity case at cube shape. So many people thought this was too difficult to do. I decided to find a way to make it work. So you need some things to do this. So for a given scrambled shape, you need some way of figuring out an even parity or odd parity. Now for the cube shape, that's well defined, it's easy. For other shapes there is no one definition, so the best way I think to solve that is just to decide what it's going to be for each shape. So pick some place for all the pieces to be, call that solved, and then find where the pieces have to go relative to those solved positions, and you'll get an answer of even or odd parity for that. And then you need some way of turning that answer of even parity or odd parity into a way to solve the cube shape and parity at the same time. So first of all, the best way I find to trace the pieces is to do a little bit like a blindfolded solve. So you'd have the cycles and you go through one target at a time. If it's an even number, you'd have even parity. If it's an odd number of targets, it's odd parity. I'm not going to explain that in a lot of detail, there's lots of tutorials out there. It's not quite the same as blindfolded. You don't need to memorise the targets or the cycles, you don't need to know how many targets there are. You're not moving pieces around inside these shapes like some sort of blindfolded method. You just need an answer of even or odd depending on how many targets there are. So for example, if I do this, in fact I'll show that. 5, 4. Okay, so I used a Sq-1 solver to solve to this position. So here we have scallop, hope you can see that okay. So I have this solved so that all the pieces are in the correct positions for where I've decided correct positions are for this shape. So the top layer has all the yellow pieces, the bottom layer has all the white pieces, and I've got the edges in the following order: red, orange, green, blue, working clockwise. Same in the bottom, red, orange, green, blue. Similar for the top, the corners, red, orange, green, blue, red, orange, green, blue. Now that's just how I've decided to do that. If you are deciding to learn this, then you can lay them out some different way. Find some way that works for you so that you can remember it consistently and know where everything has to go very easily. That works for me, and throughout the tutorial I'll just be going through how I do these things. If you want to do things differently, then watch, find out what's happening, understand what's important, and then go away, make your own notes, make your own choices about how to implement it. But this will certainly give an idea of how to actually do all these things. So one other thing I'm going to mention just now, say we have this shape here, barrel, so you've got a pair of edges there, there and there. Sometimes with a shape there's two different ways of lining it up for the first move, and those two ways are mirror images of each other. Sometimes those two ways have a different effect on parity, and therefore you need to be able to tell them apart. And so by default, I try and align things relative to one of these positions here. So it's sort of like a tetrahedron shape. There's those 4 positions where the edge pieces are, so there, 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 or there. And that will turn up in quite a few of the videos. And if I want the other way, I can just line things up relative to one of the other 4 positions. You'll notice that if I do a 6 move in the top or the bottom, or do an interchange move, those edge pieces stay in the same place, those edge pairs, ignoring the actual stickers. It's just the locations that we're worrying about here, and that's why those work the way they do. So that's something that's quite important. Sometimes it's fairly easy to see how to change parity, but sometimes it's not obvious, and that is very useful for telling apart 2 different solutions. So the way I do this is, for each shape I'll have a default algorithm and an alternative algorithm, and that's designed in such a way that it's easy to tell what the default algorithm of the 2 is, and therefore which one is the alternative algorithm. And for each shape I know whether the default algorithm either preserves parity, so if I trace I get an answer of even parity, that will give even parity in the cube shape, and there's odd parity, I would have odd parity in the cube shape, which would obviously be a bad idea to do. Or whether it switches, so if I trace even parity I get an odd parity at cube shape, or if I trace odd parity I get an even parity at cube shape. And again, you'll see a bit more of that as I go through the different cases. Okay, I have some resources. I have this Excel sheet on the speed solving forum with lots of shorthand notes which are explained. I have this text document which explains quite a lot, including explaining some of the Excel sheet. Towards the bottom I have a setup and an alternative solution for every case, so that would give you the default and the alternative algorithm for every case, a quick discussion of all of them. And I also have all the shapes laid out in a graph. That's a mathematical term of a graph, so you have a link between 2 states if they're one twist away from each other, and that basically captures all the structure. So from square square I can get to kite, and it also takes into account the parity of that, and then I can use that to find out some interesting bits of information. For example, 62 out of the 90 cases you can solve the case in the same number of moves, whether you have even parity or odd parity, and the worst case is when you need 7 extra moves, which of course is just square square. The shortest parity algorithm is 7 moves, and it also gives more useful information such as optimal solutions for any given case for both even parity and odd parity. It just gives me a list, I look through it. It doesn't tell me the moves, it just tells me the shapes, but that's enough information. I wrote some code over a few weeks which did that for me. And I'm going to finish here with some sort of example solve, which I hope will work well. So just scramble this a little bit. This is my good square one, that one's rubbish, very slow. Which is probably my fault it's slow, but that's not the point. So let's do that to sort of randomise parity a bit. So here there's 6 corners, you turn that, that's a cycle that changes parity. There's more ways to change parity in this shape, that will be discussed in a future video. And so here we have one scrambled square one, and I don't immediately know how to solve this so that I get even parity. One quick thing to mention first, there's some discussion on the forum about this, saying that for certain cases such as, well, I suppose barrel would count, or say fist, where the normal solution would be 2 moves. If you have bad parity, it would be 5 moves. And there's a suggestion that in those cases, instead of solving the cube shape and parity at the same time, then just deliberately solve with the wrong parity and then do parity and corner permutation at the same time, parity CP. That seems to be a common alg set, and this means that you don't have to inspect to find out what the parity is. You know it in advance, which would be very helpful because the main problem with parity CP is recognition time. So that's a suggestion. I don't do that sort of thing. I'm not bothered about being fast. I just do this for the fun of it. So, say I start here. I'll trace around the edges first. So, for instance, how that yellow-orange edge goes to there, the yellow-red one, and that's actually the end of the cycle. So start with 1, new cycle there, that's going there, that's O, that's even. That's actually another cycle ended. That one's going there, so now 2 cycles, so I count 1. So currently an odd parity. I start with corners, start with this one, that one's going there, O, 1, O, 1, O. Okay, so ended on O, or 0 if you prefer. I go with O because it's 1 syllable rather than 2, it flows better. And if I have even parity, then it means I have to change the parity there. So now, relative to how I define this case, this is odd parity, but that should mean that once I get to cube shape, parity is even. Oh look, and it's solved, no parity, done. This can be done fairly quickly. I've attempted this in competition, inspecting within the allowed 15 seconds. It went decently well. I got 7 out of 10 successes. I messed up some of the cases, which was silly. I've since posted an average of 5 that was successful on YouTube. It was sub 20, with untimed inspection because I was out of practice. But yes, with enough practice, this can be inspected fast enough to do it in competition. That's what I wanted to show. I haven't shown that conclusively yet, but I think I have shown that it's certainly possible with enough effort. And the rest of the videos will then just be talking through all the different cases in a bit more detail, showing some of the solutions and certain things to watch out for. And as soon as they're all done, I will upload them. I probably won't start uploading them till they're all finished, and I'll be changing some of these notes here, uploading them too, so these will be slightly different by the time they're next uploaded. And yes, you're learning this. Good luck. Well done to you. You're very cool for learning this, and thanks for watching.